propose to your advisor, you have this problem, and then your advisor will ask you, can you propose some idea? So how can we solve this problem? You say, oh, it is okay. If I can put free-filling tile here, if I can put free-filling tile here, maybe I can solve the problem. So if the current goes here, then you turn off Q1 and then you turn off Q2. Then the diode will automatically turn on, right? We can go to the diode. If the current is go this way, then we can go this diode, right? So the current go this way, this diode automatically turn on. The current go this way, this diode automatically turn on. Then we solve the problem. Okay, we say, oh, it is good. And we can turn off the diode. So this is D2. So this is D2, automatically turn on. So you can see the D2 will fill this space, right? So the D2 is ideal, then no problem. But do you get any ideal diode? What is ideal diode? If you want it turn on, it immediately turn on. Do you think your diode will cause some delay? Yes, because it is physical diode. So if you have a very physical diode, it could be like this. It creates delay. So if it creates delay, then what happens? During this turn off, and the diode not turn on yet, then what happened? No path, right? No path. So now you turn off Q1, you can turn off Q2, but the diode wait for 1 microsecond. But now you are waiting, so diode not turn on yet. Then everything turn off, then spike, right? So you still create spike. So you think diode can improve because it can improve this time interval, but not improve whole interval, right? So after you try diode, you say, I'm sorry, it doesn't work. Then what can you do? So now you have to put some location to observe the energy, right? Because you have inductor energy. Inductor energy should be go somewhere. So if you have a flooding, the level of the river increase quickly, then you have to create some maybe lake or some river to get the water flow out. Otherwise, this is city. The water will go to city, and every home will be flooded, right? So we have to find a way to let the current go through. So how can you do this? So there is one way. You say, oh, I can put a capacitor here. So maybe a capacitor here, capacitor here. And I can put a resistance here to limit the current go to the capacitor, not too huge, right? Then after this turn off, this turn off, this turn off, then you have current here. Maybe you have current, we say, go this way, then what, or go this way. Then what happens? You have current go this way, then the current can go to the resistor, to the capacitor, and charge the capacitor, right? So the capacitor can observe the energy, right? Then it is okay. So you create a leg here. So if the time from interval, then every water go to the leg, and the leg is huge. So the leg water level increase, but no problem, right? No problem. So now you create a capacity here, and then you say the current can charge the capacitor. If the current charge the capacitor, how about the capacitor voltage? The capacitor voltage increase. So the capacitor voltage increase. And the next time you charge again, so the capacitor voltage just like this. Increase, 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 then become infinity. Then one day the capacitor burn out. So you have a garbage dump. Every day you put garbage, and then tomorrow you put another garbage, and then after 1 month it become a small mountain. After 1 year become a big mountain, right? Because you always dump. So if you always dump, then the voltage become infinity. Then it damages the capacitor. So what should you do? If you have a garbage can, you can dump garbage, but during night you have to burn. And then next day it become empty, right? Then you can dump again. If you have a leg during typhoon interval, you can get the leg water level become higher and higher. But after the typhoon, the leg should be spread water to the city. Then it is okay, balance, right? So what should you do? After you dump, next time, when the switch or this switch turn on, then you have to create a diode here to make the voltage go through here to release the energy, right? So increase voltage, but when next time it turn on, I can use the voltage to go this way. Then I reduce the voltage. Then your voltage increase and decrease. Increase and decrease, then balance. So what is this snubber? It is like a leg. So I observe the energy. When the switch turn off, I get energy. When switch turn on, I release the energy. Then get energy, release energy, get energy, release energy. Then I'm okay. So then we can have a very brief conclusion. If you have inverter here, this is ideal inverter. How many switch do you use? 6 switch. So your motor is here. Your motor is here. Your motor is here. This is A phase, B phase, C phase. Then this is your neutral. Then, in order to get the energy balance, you had better put free-filling diode. So after Q1, Q2 turn off, you can go to the free-filling diode. But before your filling diode turn on, you have some energy. The energy should be dumped to capacitor. So you have to put snubber here. So you have to put capacitor here, resistance here, and then diode here. So we call this snubber. So each switch needs 1 snubber. How many snubber do you need? 6. So you need 6 snubber. So we need 6 snubber. Six number. So you can see this is device, this is device, this is device, this is that device. So you have 6 device. But you have RLC snubber here, snubber here, snubber here, snubber here, snubber here, snubber here. So you become huge. But what is power electronics small size? Then you become huge, huge size. What is power electronics? Reliability should be better. But you put so many devices, and this device create heating. Is it good? No, it is not good. So you see, it is messy. It is headache because you have to put a lot of device here. So you can see 1, 2, 3, 3, 6, 18 devices. So you have to work for this 18 device. So it become headache. So why? Because you need to take care of the spike. So how can we select the resistance? How can we select the capacitor? How can we select the diode? If you put the capacitor too small, then what happens? You turn on, turn off. For example, turn on, turn off. So maybe you have voltage here. If you do not use any snubber, then the voltage is like this. So this is 200. This becomes 800. Minus 800. This is minus 200. Then you can see it is huge voltage, right? Short, but huge. Then what happened? Damage this one, this one, this one, this one, this one, this one, without any smoke. Nothing happened, just damage. So if you burn on, burn off, if you burn an IGBT, you can see the smoke because too hot, because temperature is too high. But if it is due to spike, no smoke, just damage. Then you replace again, damage again. So because the spike. So then you design the snubber, but you choose a small sheet. Then the voltage become like this. Like this. We just see before, right? For example, like this. So we call this is greening. So how can you solve greening? You can increase capacitance or you can increase resistance. If you increase resistance, then it become like this. Because you use your resistance to overload the energy. So the resistance can get the energy. But the resistance become high temperature, heating. But it can absorb the energy. So you can increase resistance to get depth. To increase depth. So we call this depth. So if you have a swinging, this one, you increase depth, then they become only one type. So we call this depth. If you drive a car in the snow, then your car just rotate. Then you can put something to depth, increase the depth. So we call this is the depth. But if you put the resistance too much, then what happens? Your circuit just like this. It becomes too slow. So before, this is what you want. But now, it delay a lot of time. So this is not good. This is also not good. We call this is over depth. We call this is under depth. So you have to careful design the snubber. If you put too small resistance, then it reading. If you put too much resistance, it overheat. If you put an optima, it is like this, then it is perfect. So you have to carefully design. But if you design electrical vehicle, you put so many snapper, do you think this is good for your electrical vehicle? Not good, because reliability is not good, right? Too much. Then how can you solve this problem? Then some businessmen, they found some way. If you have this line and this line, what can you do? You have to use a line between here. If you use this line and this line, you have to put a line. But a line is equal to small inductor, right? A lot of inductor here. Then you see the waveform is not good. So how can you improve your system without straight inductance? I hope I don't have any straight inductance. So I don't need a line. So I have to remove line. I cannot use line, because a line here from here is equal to one inductor, right? So I have to avoid to use the inductance. How can I do this? So we create bus bar. So we call it bus bar. What is bus bar? It is a couple and a very thick, very thick. And I put a hole, so you can put your device direct to the bus bar. Then no inductance, because resistance, it is only resistance. Resistance is related to area and length and the area. If the length is longer, resistance is larger. If the area is larger, resistance is smaller. So they put a lot of area. This is large, this is small. Then resistance is almost zero, right? Almost zero. But it is expensive. And we do not use any line. It is couple. Couple has no inductance. So if you see the electrical vehicle, they don't use any line. They use bus bar. And from here, you can see bus bar. And this one here, this one here, and here also bus bar. This one here, this one here. From here to here, also bus bar. So no line, no line. So it is important, but it is expensive. So now people use a lot of bus bar, especially for what? High power, like electrical vehicle, renewable wind generator. They have to use bus bar. They cannot use wire. Wire is not good because wire is inductance. Inductance creates spike. Then you have to avoid to use the inductance. So we call this is a snapper circuit. So we finish the snapper circuit. Then we will move to the current source inverter. So we have another video that discuss about current source inverter. So what is inverter? How many types of inverter? Two types. Called voltage source inverter, current source inverter. Two types. What is voltage source inverter? How can you do the modulation? So we have 6-step modulation. We have sine wave, PWM. We have space vector modulation. We have hysteresis control. We have triangular control. we have predictive control. So we mentioned about VSI, a lot of modulation method, right? So what kind of application is VSI? What kind of device can you use? You can use IGBT. You can use MOSFET. You can use silicon carbide. So you can use power device, high frequency, right? High frequency. But what is current rate? What is the current of IGBT? How many current can you flow? So you can say it could be 200 ampere. But now, I want to work at a power system. I need 10 kiloampere. Can you provide 10 kiloampere for wind generator? I need 10 kiloampere. And for some steel company, steel manufacturer company, they need 10 kiloampere. For power system, they need 10 kiloampere. But can you provide 10 kiloampere for IGBT? No. Then how can I design this system? So I need a wind generator. I need a water pump storage. I need 10 kiloampere. This is the basic requirement. I have a static valve, the reactive generator. I need 10 kiloampere. So in power system, every unit needs 10 kiloampere. I need huge current. So can I use VSI? The answer is no, because your device only maximum 200 ampere. So in this case, what can you do? You have to go CSI. So this is a high power application. Like power system. Like HVDC. Like steady. What should we do? We need a current. Input current. So our input is not voltage. Before we have a voltage, we say we have a voltage. We use a capacitor. Then we change the voltage into current. So this is motor. So A phase, B phase, and C phase. But this is voltage. So we call this is VSI, right? VSI. Now what do we need? We need current source. This is current source. And we put the current source into 3-phase. And then we output 3-phase current. So this is 10 kiloampere input current. So now I ask you one question. How can you buy 10 kiloampere DC current? Can you buy it? Anyone sell it? Can you go to 7-Eleven, say I need a 1 ampere battery? No. Why? Why not? You only can say I want 6 volt battery. But you cannot say I need 1 ampere current. But in your circuit, you always see this one. So when you study electrical circuit, right? It always teach you, or you have 10 ampere current source, right? So what is current source? Can you buy a current source? If you cannot buy a current source, how can you design current source in water? So anybody has any idea? What is current source? So we cannot buy a current source. If you cannot buy a current source, how can you create a current source? So if you learn operation amplifier, what is operation amplifier? You have 2 transistors, you have resistance here, you have current source here, right? This is differential amplifier, right? So how can you design with current source? If you cannot design current source, you cannot design differential amplifier. If you cannot design differential amplifier, you cannot design operation amplifier. So how do you learn operation amplifier? You say we can design a 1 milliampere current here. So from here, 0.5 milliampere. From here, 0.5 milliampere. So if I change the input, then I can change the output, right? So now I ask you, how can you design 1 milliampere current source? You have to design, right? Otherwise, how can you design differential amplifier? So we have to design current source. So how can we design a current source? We cannot buy it, but we can design it. So how can we design it? In general, we use HCR. So we design HCR. So we have 3-phase input. We have 3-phase output. So this is output. So we call this is VR. So we have 3-phase output. So we call this is 3-phase AC to DC phase control, right? Not rectifier, but phase control. So we can control the phase, the delay angle, alpha. Then we can calculate the VR is related to alpha, cosine alpha, multiplied by something. So we can adjust alpha to adjust VR. We call this is phase control. Converter. So we can adjust VDC by control the delay angle, right? So if you have HCR, then what can you do? Then you can use AC, you design HCR to control the load. So you can adjust the alpha. Then your output could be like this. So you can control alpha to control output, right? So we can see the output is related to alpha. So no problem. And then we can put huge inductor here. Very huge inductor. So if you open the CSI, you see this is CSI. This is inductor, this is circuit. Inductor is so huge. If you open VSI, you can see this is capacitor, this is circuit. Capacitor is so huge because you have to store energy, right? So we have a huge capacitor. And then what? You have a switch, thyristor. So the structure is like this. Then we have a motor. We have a motor. But now, here we need 100 ampere. So it is like this. So the input is 100 ampere DC current. Then we convert the DC current into AC current. So we call it is current source inverter. So if you compare to the voltage source inverter, it is like this one. We have diode. We have diode, 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 diode. So we have 3-phase input, but we use diode. Then we have DC voltage. Then we have 6 switch. Then we have motor. So this is VSR, and then this is CSR, right? So we call this is duality. What is duality? if you have white, what is the duality of white? Black, right? If you have resistance, inductance, what is the duality of inductance, capacitance? If you have voltage, what is the duality of voltage? Current, right? We call this is duality. So if you have dividing theory, then you have duality. Norton theory, we call this is duality. If you have a loop, what is the duality of loop? We call knot, right? So we have duality in electrical engineering. So if we have voltage source, what is the duality of voltage source? Current source. Current source. So the structure is like this. But now we need to create input current, constant current. How can we create input constant current? So then what do we need? We need a sensor. So this is IS. And we have desired current, IS star. So we have desired current 1000 ampere. We have real current. Then we can control alpha, the firing angle. Then we can control the firing angle to control the VR. So now it is like this. So we have command here, 1000 ampere. This is our command. And this is real current. So at that point, we said we need 1000 ampere, but at the beginning, 0 ampere, right? Because it is begin. Then what should we do? Should we increase voltage or decrease voltage? We have 1000, but now we only have 0. The error is 1000. If we need 1000 ampere, then should we increase the voltage or decrease the voltage? Increase or decrease? If you decrease, become 0, then you never reach 1000. 1000 ampere. So if you need 1000 ampere, you have to put the resistant voltage, the VR, as high as possible. So we have a high VR. So we have to control alpha to control VR. So we have a very high VR. Very high. If we have a very high VR, then this is VI. This is VR. So we have VR minus VR minus VR. VR. So it is equal to inductor voltage, VL. This is LdI Ldt. So we have dI Ldt is equal to VR minus VI divided by L, right? But now VR is larger than VI. So this is positive. This is positive. Positive divided by positive become positive, right? If the dI dt is positive, the current will decrease or increase. If this is positive, the current will decrease or increase. If you think increase, please raise your hand. If you think decrease, please raise your hand. If this is positive, then the slope is positive. If the slope is positive, the current will decrease or increase. Increase, right? So you can see this is larger than this. This is positive. This is positive. positive divided by positive is positive. dl dt is positive. When t is increased, IL is increased. So the current will increase. So the current increase, right? And after the current reach more than 1000 ampere, it is too much. So after that, you have to decrease the current. So here we keep VR. If you want to decrease the current, what should you do? If this is larger than this, current always increase, right? Now you need to decrease your current, so VR should be what? Reduced. So if you need to reduce, then your VR should be reduced. Then you found that your current is too small. Then what should you do? You have to increase again. If you want to increase, then your VR should be increased, right? And then you found that it is too much. So after that, I needed to decrease. If I decrease, then I needed to decrease the VR. So the waveform is like this. It is like this. So we can control the input voltage to control the current, right? So what do you need? You need a control. So you need a feedback. So you have to detect this current sensor. You have a current command. So you have current error. If the current error is positive, which means you need more current. If you need more current, you have to increase VR. Then current increase. And then you found that you are too much. Then you have to decrease your VR. Then the current will decrease. So you can control the input voltage to control the input current. So you can see we can get the waveform like this. But now you see the ripple is too much. The ripple is too much. If I want to reduce the ripple, what can I do? So when you want to increase the current, then you have a very huge VR. So dIdt is VR minus VR divided by L. So VR should be larger than VR. Then you can increase the current. So current will increase. If you want to decrease current, so you have VR minus VI, it is L dIdt. But now VI is smaller than VI. So then dIdt is equal to VR minus VI divided by L. But VI is smaller than VI. This is negative. This is positive. Current will decrease, right? So if I need a very smooth current, should I increase the inductance or decrease the inductance? If the inductance is infinity, then the slope is very small. If the slope is very small, then what happens? I have a current like this. So it is better, right? So if I need a small ripple, should I increase the inductance or decrease the inductance? Increase. If I can put the inductance 1000 times, then the ripple becomes 0.1%. So if we want to design a current source inverter, we have to design infinity inductance. But how can you design infinity inductance? It is too big, right? So we only have limitation as large as possible. So if you open the current source inverter, you see a huge inductance. This is CSI. Why you choose a huge inductance? Because you need small ripple, right? So we can see this is the current source inverter. So the current source comes from your design, not come from supermarket. You cannot buy it because you have to design it. Then if one day, what is the disadvantage of the current source? You need feedback. So this is CSI. How about VSI? VSI use rectifier. Rectifier. And the capacitor. Do you control the VDC? No. You just design it. So sometimes if you put heavy load, then the VDC originally you want to 600 volt, but now drop to 500 volt. Do you care about it? No. You don't care. So for VSI, no feedback. We just let it go. So no feedback for VDC. For CSI, you need feedback for AS. So you need to feedback. So it becomes more complicated. If one day this line broken, then what happens? One day, some mouse eat your line, and this line broken, and you set 1000 ampere, but the feedback 0 ampere. So you need more current, right? If you need more current, you increase the VDC, and then still 0, increase the VDC, still 0, increase the VDC, then you damage your circuit, right? Because it becomes infinity. So it is not good. So we need feedback. If the feedback is fair, then your system damaged. So you can see CSI is more challenging than VSI. So if you do research, do you like to do CSI? So you have to control a current, constant current, and then you spend 1 year to design this circuit. Then everybody graduate, you still working. So do you like to do this? No. So only a few people like to study CSI because it is too complicated. So the CSI is like this. So it is for high power application. We use HCR, we use Syreston for the CSI. So now we want to discuss about how can we determine the switch. So we assume we can control the VR to get a constant current. So now we have 1000 ampere constant current. So now we have constant current of 1000 ampere, and then we have 6 switch. And then we have AC output. So we want to discuss ABC phase. So this is our structure. So how can we design the switch? So this is the issue. So we want to design the T1, T1 prime, T2, T2 prime, T3, T3 prime to obtain the 3-phase output. So we call this switching states. Of CSI. Okay, so now we have 1000 ampere here. We have T1, T1 prime, T2, T2 prime, T3, T3 prime. So we have 6 states. So we need A phase, B phase, C phase, and then we can have minus B, minus C, minus A. So totally we can have 6 steps. 6 steps. So how can we control the 6 steps? So if we have 1000 ampere here, then what can we control? What can we control? So we have 1000 ampere here. So first we can turn on A phase, and we can go this way, go back to B phase, and then return. And the C phase is here. So we call this A to B, AB. And the next step, we can go this way. We have A phase, we have C phase, we have B phase. We can go this way, AC. And then next step, we have B phase, we have C phase, we have A phase. We can go here, so it's BC. So AB, AC, BC. And how about the next step? Next step, BA. BA. So this is C, so we have one source here. So B to A, so BA. And the next step, CA. CA. And this is B. Like this. So CA. And the next step, CB. CB. This is A. So we go this way. C to B. This is A. CB. So we have 6 steps. So if we see the current A phase, B phase, C phase. So we have current here, we have current here, we have current here. So we have 6 steps. So we have 6 steps. So at the first step, A, B. So A go inside. If you go, this is nature. If we have current go from A to N, do you think A phase is positive or negative? You have a motor, then we have 1000 ampere go into A phase. The current is positive or negative. So you have a motor. Now we have 1000 ampere go to the A phase, and then we from B phase to go output. So this is 1000 ampere. So if you have current go flow into A phase current is positive or negative? Positive or negative? If you have a load, this is input. We have 10,000 ampere go from here. Do you think I/O is positive or negative? Positive, right? Because it is load, and the current go to load, it is what? Positive. So this is A phase. Now the current go to A phase, it should be what? Positive. So A phase is 1000 ampere. How about B phase? Now we go from here. So if you have a motor, we go this way. So how can you call this? Minus 1000 ampere, right? So it becomes minus 1000 ampere. So we can draw this way. How about, sorry, this is B phase. B phase is minus 1000 ampere. Minus 1000 ampere. How about C phase? C phase is here. 0. No work, right? Because it is isolated from the CSI. So C phase is 0. here is 0. So 0 ampere. So we can draw A phase 1000, B phase minus 1000, C phase 0. So we can have 10 minutes break and we will draw the next step.